Okay, so we'll continue section 6.1. Yesterday we studied the technique of integration by parts for indefinite integrals, and today we will continue with definite integration. So, as you can see, the continuation, definite integration by parts, it just means that you have an integral of the form from A to B, because it's definite, of the form u dv. And it just means that you will apply concretely the formula of integration by parts with the limits of integration, ub minus integral b dv. Okay. So the formula is still valid because it comes from the derivative of a product. It's just that you have chosen your definite limits of integration. And again, as in many parts of this course, we learn by example. So we will do the first exercise 6.1.4, which is to find the area using integration by parts. In fact, look, we will use the phrase integration by parts very commonly. And when you go into higher mathematics, there's a way to write it shortly, which is IBP. We'll save you some time, and you might get used to it. Just as a comment, actually, well, even if you later on were to do a computer code based on some numerical techniques different than finite differences, there are techniques for numerical integration that are based on integration by parts. If you have ever heard about the finite element method, which for engineers is very common, the whole method is based on integration by parts, just to let you know that it's important, even when you code. So you have the area of a region which is bounded by the curve y equal natural log of x, by the x-axis, and by the line x equal to e. I'm curious, who has seen integration by parts in definite form before? Can you raise your hand if you have seen this before? No one? Okay. So let's draw the figure. My personal suggestion for the topic, especially for what we saw last time, is that you do several exercises to practice. If it's really the first time you have seen it. Because the only way you will develop an intuition into how to solve these problems is by practicing. So you have the curve of the log, which is the inverse of the exponential, so you kind of already know its shape by an inverse function kind of argument. So this is 1, natural log of 1 is 0. You have the x-axis, you have the y-axis, you have the curve y equal natural log of x. And it's the region bound by this curve, the x-axis, and by the line x equal to e. So that means that you have to go over here and you care about this a. Okay? So, of course, for the domain of interest, natural log of x is greater or equal to 0 for the points in the interval from 1 to e. E is around 2.7 below. So, what you have is that the area that you care about is the integral from 1 to e of natural log of x dx. Now, we have done several examples of integration by parts for indefinite integrals before, and this one is easy. We kind of like know the answer. We probably even did that one. If you think about it, if you take u as natural log of x, the derivative of u is 1 over x. So this is one of those. In fact, we did one which had a different factor, but in any case, this will be your u, this will be your db. U is equal to natural log of x, so that means that the u is 1 over x dx. Think about it as the derivative times the differential factor. db is equal to dx, so actually what you know is that b is equal to x. If you want to write it formally, b integral of dx is equal to x. So now we do integration by parts, right? So the integral from 1 to e of natural log of x dx is the integral from 1 to e of the function u db with the definitions that we had over here, which is equal to u times b from 1 to e minus integral of b du from 1 to e. This is just the integration by parts formula we saw yesterday with the definite limits of integration. So we just have to plug in what we have, what is u, what is b, what is du, and what is db. So u is equal to natural log of x, b is equal to x. This is from 1 to e minus integral of b from 1 to e du, which is 1 over x dx. This is nice because you get a cancellation, right? So this is pretty convenient. You can actually start to do the evaluation, or you can simply x natural log of x, and you do it in 1 second from 1 to e, minus the integral of the x from 1 to e. So, well, this also simplifies very nicely. Yeah, because this is the integral of x. So, in fact, well, I mean, you could have x natural log of x minus x, all these from 1 to e, and you could even factorize this x natural log of x minus 1 from 1 to e, if you want to simplify your life. So at this point, you can do the computations, which is e times natural log of e minus 1 times natural log of 1 minus 1. So some of these terms will vanish. In fact, natural log of e is 1 minus 1 equal to 0. So then basically you have this is 0 minus minus, so plus 1, so this is equal to 1. And you're done. Okay, so there was a reason I spent a couple steps shaping this in a nice factorial form, so that I will have some vanishing which happened. Natural log of e is 1, so that cancels out. That one is 0, minus minus plus, you're done. And so, yeah, I mean, this is one example where you can use the definite integration by parts in order to compute something physical like the area. And now we come to an example related to your disciplines. So it's something related to business, which is example 6.1.5, which is related to calculating the future value of an investment. So we have to remember what we have done in previous sections, and we'll also spend some time in developing the statement of the problem because it's important to solve it. The general guidelines are the following. You have a 5-year investment, and what you care is that t years from now it will generate a continuous income stream. So be mindful of the income stream, because that will be, in a way, kind of like a function related to the derivative in a way. And that continuous income stream is given in a mathematical form, 3,000 plus 50 times t. Now the units of this is dollars per year. What you also know from the statement, so this is one point, the other point, third point. The prevailing annual interest rate is fixed at 4%, and you will do a continuous compounding during 5 years. So, the question is, what is the worth of the investment in 5 years? And we have to recall what we had done in previous sections, especially 5.5, where there is a formula for the future value. In fact, let me write it over here. So future value, let me write first the formula and then I will do an explanation. So you'll have the integral from 0 to t of a function f of t times e to the r times capital T minus t dt. So fb is the future value. This t is the term. You have a term of t years, so t is equal to 5. F of t is what it's been called as the rate of the income stream deposited continuously. which is basically the function that you were given. So f of t, if you want 50t plus 3000. And then you have a rate. So R is the annual rate, which is of 0.04 since it was 4%. So look, if you want to recall this is in section 5.5. And let's just interpret it physically for a second. Has it been focusing all the time? Or it's okay? Okay. So basically this is the amount of money that you will get after 5 years. So you integrate the whole effect. This is the rate of income stream, but then you have some exponential accumulation due to the continuous compounding where you have the rate of interest, and then this is working inversely, so that's why you have the t minus t. If you want to know more about the theory, it's 5.5. We have seen some of these topics before. But essentially, it's how to get the whole amount of money in that period, which is what we care. The key information is precisely this function f of t that is given by the problem. And the example again is chosen appropriately so that we can practice our integration by parts. That is, at the end of the day, the motivation. Of course, there is context, there is application. In your own subjects, you will have to basically incorporate the applied part, but in terms of the math, this is what we care. So if we plug in all the values that we have, t is 5, then you have the function, which is 3000 plus 50t, then you have e to the 0.04 because of the rate, and then you have t, which is 5 minus t, okay, and then dt. Okay, at this point, the question stops from being applied and is completely mathematical, and it's simply a definite exercise of integration by parts. Clearly, you have a linear function and you have an exponential, and we have seen this kind of argument before, right? The whole idea of integration by parts is basically to rephrase the things into a new integral where the new integral is easier. If you consider the derivative of exponential, you will get the same except for a fact. If you consider the derivative of a linear function, you get a coefficient which is constant. So it's clear which should be our choice of u and p. The linear function should be u, so that we have the u in the other integral and everything is simpler, and then you will have the exponential anyways, which is simple to do. That is the whole strategy. So the motivation is that u will be the linear function. This will be my dB. If I do the computation, I have that u is equal to 3000 plus 50t. If I take the derivative, this is 50 dt, because I have a linear function, right? Slope is 50. Then I have dB, which is the exponential of 0.04 times 5 minus t dt by choice. So basically I have to integrate. So b would be equal to the exponential of 0.04 times 5 minus t, but I have to incorporate the factor. And it is minus 0.04 because if you actually look at the coefficient of t, you have 0.04 and then a minus sign. So think of that function, take the derivative, the factors balance out. Okay? If you actually shape it in a nice fashion for the denominator, you have minus 25 e 0.04 times 5 minus t, because the inverse of 0.04 is 25. Okay? So we're just choosing appropriately, and then we will do some manipulation. So the thing is, in the form that we want it, it's basically what you have is the integral from 0 to 5 of a function u times dB with the functions u and b of choice that we have indicated over here. So this is integral, well, the integral of this is equal to u times b evaluated from 0 to 5 minus the integral of b du from 0 to 5. At this point, this is just an integration by parts formula. One second, please. Okay. So we plug in what we have. So u is 3000 plus 50t. Then b is minus 25 times e to the 0.04 times 5 minus t. That is evaluated between 0 and 5, minus the integral of b, which is minus 25, exponential of 0.04 times 5 minus t, du, which is 50 dt. And evaluated from 0 to 5. So, again, what we predicted happens to be true, right? Okay, that is just an evaluation. On the other hand, the coefficient, which is the du, is related to the 50 dt, so that's just a constant factor, and then you have the integral of an exponential, which can be performed easily. So you're done. So at this point, it's just to compute. We just have to finish the computation. If you think about it, you have the minus 25 as a common factor. So this is minus 25, multiplying, well, functions. Then we will do the evaluation. So 50 times 5 is 250. Be mindful that actually when I evaluate the exponential of this form at 5, this is a factor of 1. So look, the minus 25 is here. This is 1 for this evaluation, so I don't have to carry it. So I'm covered in that aspect. And then, on the other hand, when this is 0, I just care about this factor. This factor is taken care of. This is exponential of this stuff. So this would be the 3000, because here I don't have to care about this term. Then I have e to the 0.04 times 5. Okay? So I have taken care of all the factors at this point. I will also incorporate this factor, well, if you want, I have the minus from the minus 25. So this is this, and then I have the other integral, which I can perform. So this is a definite integration where I have e to the 0.04, 5 minus t. I still have to incorporate the factor, so it's now performing just the integral of the exponential. So this is minus 0.04, and this is evaluated from 0 to 5. And there is a factor of 50 over here, so I multiply by 50. Okay? So I have been careful into incorporating all the factors. This minus is from here, this is from here, this is from here, this is just evaluation. Okay? So I have done this because these two had the factor of minus 25, so of course I want to basically just factorize everything by that to take care of that at the end so that I don't have an issue. Then this is 3,250 by doing the addition. Then I have minus 3,000 times exponential of 0.2 if you do the multiplication. Then you have this factor taken care of. Then you have the minus from these two. Then you have 50 from here. Then you have the 0.04. So you'll have to still do a computation. And then you do the evaluation of these two. So the minus 25 went over here. Here you will have a vanishing, so you will have 1. Then you have minus e to the 0.04 times 5, which you already know it's e to the 0.2, but okay, just to indicate that we have done the computation and we have taken care of the factors. So finishing the computation, this is minus 25. Then you have 3,250 minus 3,000 times exponential of 0.2. Then you have this factor, 50.04 of 1 minus exponential of 0.2. So the reason I'm kind of like waiting for this computation is because I recognize, look, well, here I will have 50 times 25, so that will give me some big number, but what I can do, or what I will do at the end of the day, is associate the numbers which are related to the exponential of 0.2. So this is minus 25 times 3,250 minus 3,000 times exponential of 0.2 plus 50 times 25. If you remember, the inverse of 0.04 was 25, and then 1 minus 2.2. I'm going step by step just to have everything with me, or everybody with me. So this is minus 25, 3,250 minus 3,000, the exponential of 0.2. This is 1,250. And this is 1 minus exponential of 0.2. At this point, okay, there are 2 more pieces in the cake, which is basically associate these numbers and then finalize the computation. So I would have minus 25, 3,250 plus 1,250. Then I have a factor of minus in both, exponential of 0.2, and then this is 3,000 plus 1,250. So, okay, yeah. So this is minus 25. Here I have 4,500 from these two, minus exponential of 0.2 of 4,250. So actually what happens is that this factor is bigger than 1. So that will make, considering this sign, everything positive, right? If you think about it, the functions that we use to start to integrate, well, this is positive in the interval under consideration, and the exponential is always positive. So we can only have a positive result at this point. Okay, if you think about this factor of exponential of 0.2, this is around 1.22, blah, blah, blah. If you do the actual computation, well, you could flip the signs if you want. 25 times exponential of 0.2 times 4,250 minus 4,500. And then you can finalize the computation. This is 25 times, and if you do the computation, this is 5,190.96 minus the 4,500. So you have 25 times 690.96, which if you do the computation is 17,274.043. And so if you have it in the unit of dollars, this is around 17,274. Okay, so you're done. So just be mindful, you are not going to get something negative, because essentially this factor is bigger than 1. It makes this whole number bigger than 4,500, and then you will end up with something positive in the overall. So be mindful of the signs. I did a flip in the signs so to have everything in a nice fashion, and then I finished the computation. But okay, in any case, this is an application where given that we have the product of an exponential times its function f, which represents the income stream, you have the integral of a product, which can be put in a nice form by integration by parts. So there can be applications where the definite integration by parts can come up. So the next example, it's basically that, look, sometimes you have to do integration by parts twice in order to do the computation because, well, think about it. Let's say that you have a polynomial and you have an exponential and you have the integral of that stuff. You know that for the exponentials, the derivative is basically the function itself times a constant. However, for polynomials, you take the derivative of a polynomial and you reduce the degree of the polynomial by 1. Let's say that you start with a high degree polynomial. So the idea, if you have, let's say, the integral of a polynomial times an exponential, is to do integration by parts repeatedly in order to decrease the degree of the polynomial, and so that it becomes simple enough that you can perform it. That is the whole idea. So in the next exercise, where we will perform a repeated integration by parts, let's see if I have enough space for this. Actually, let me use a new page. So, the comment is that we will do a repeated application of integration by parts. Okay. The example is 6.1.6. It's the same. You don't have to write again, it's just the same that I wrote 1 second ago. So, the concrete example that I am talking about is x squared times e to the 2x dx. Now, again, my point for what I was stressing before. I have a polynomial times an exponential. If I choose u as x squared, when I have du in the next integral, this will be of degree 1. Because I will have x times a factor. If I do that again, then I reduce it to an exponential. So that is the strategy. If you have basically functions to be integrated, which are of the form a polynomial times a simple exponential. Try to choose the u as the polynomial so that you decrease every time, and you have to do it repeatedly. In this case, because you have x squared, you will have to do integration by parts twice. So, just as a comment, essentially this is u, this is dv. By the same argument I have said before, u is equal to x squared, which means that du is equal to 2x dx. So I'm already seeing that I'm going to have a decrease. This is essentially what I have mentioned. When I have the du, I will have a linear function because it's 2x times dx. Then I have the dv, which is equal to e to the 2x dx. So I just have to integrate in order to get b. So this is the integral. b is the integral of e to the 2x dx, which is e to the 2x divided by 2. I omit the constants. I don't care about them right now. First of all, this is a definite integral. So that would be put at the end. Second, I verify, right? So I have b. If I compute db, basically you have a factor of 2, which cancels, so everything is nice, and then I have the dx. So you're done. So, if you have the integral of x squared e to the 2x dx, again, you have u times b minus b du. So at this point, we will omit it because we saw this yesterday. So this is my u times b minus integral of b du. In fact, I get a cancellation of the 2, so that's pretty neat. So this is x squared e to the 2x over 2, which represents the product ub, and then minus the integral of x exponential of the 2x dx. So this is my b du. Now, first comment. Now it's evident what I had been stressing before. We went from a polynomial of degree 2 to a polynomial of degree 1. So it was simplified. Second, what would be the strategy to do that one? To do integration by parts. In fact, that exercise was done yesterday. So the technique to do it would be, again, choose the u as equal to x, db e to the 2x dx, and iterate. Fortunately for us, we did that exercise yesterday, so we can just plug in the formula. So the comment is that essentially, okay, for this integral, you can calculate it using integration by parts again. So IBP stands for integration by parts. And if you remember, we found in the exercise 6.1.2, again, the way we did it, which was actually 2 days ago, I'm sorry about that. Integration by parts. We did the exercise and the integral of x e to the 2x dx. This was found to be 1/2 of x minus 1/2 multiplying e to the 2x plus a constant. So we're just going to plug in this. If you don't believe it, check your notes from 2 days ago. And in order to do the formula, integral of x squared e to the 2x dx, this function, which is the ub, x squared e to the 2x over 2, minus the integral of this result. So I'm just going to substitute 1/2 of x minus 1/2 exponential to 2x, and then plus a constant. The constant is not determined, so it doesn't matter if I multiply by a minus. It's still a constant, which I don't know. It will only be determined by initial conditions for the problem. In fact, I could do a factorization of this. This would be 1/2 of x squared e to the 2x minus, and then you have x minus 1/2. I could factorize also the exponential plus a constant of integration. So you would have, well, exponential to the 2x divided by 2, x squared e to the 2x minus x plus 1/2 with the minus minus, plus a constant of integration. Sorry. This doesn't go. That's why I factorized this. Okay. The whole idea, or the moral of this exercise, is precisely that now you know a technique in order to reduce integrals of this form. Sometimes you have to do them repeatedly. If you do repeatedly integration by parts, my suggestion is that be sure that you're actually reducing the integral. Because look, you can go both ways on integration by parts. One possibility is that you actually increase the degree of difficulty. Can I continue? Can I continue? Yes. Okay. Just please look. I can hear you. You distract me. If you don't want to be here, you can leave. It's okay. But just, you unfocus me. If you keep talking and talking and then I make the silence so that everybody stops talking and you continue, you are really distracting. So just do not continue. Okay? So, the exercise was performed here. My suggestion is that you have to be careful into not increasing the degree of difficulty. If you can see from the integrals from these polynomials, if you do the appropriate choice of u and b, you can decrease the difficulty, but you have to be careful in general when you do repeated integration by parts. So, the last comment on this section is, look, sometimes the amount of time that my math course will spend in integration is of the order of 1 month. And a good amount of that material is basically to review a lot of integration techniques. That is not the scope of the course. So the information that you're given in this course is to know that there is a table of integrals available to which you can go in case you bump into more complicated functions, which is perfectly fine. Sometimes the integrals can be too complicated. And that table is in your textbook. In fact, I will show it to you in a second. But the summary is that you can use integral tables. So sometimes you may encounter an integral that can't be handled with basic formulas. We will see some examples. Or either with substitution or integration by parts. One example is e to the x divided by x dx. That is not easy to perform. And in any case, the idea is that all of the integrals can be found by using a table of integrals, which is in your book. It's the table 6.1, which is in pages 488 and 489. That is, of course, if you use the edition of the textbook that you were indicated in the semester. If you have an older edition, such that perhaps it might be available on the internet, this is what you would see. So just wait 1 second. Look, well, this is the PDF of an older edition of the textbook, right? So if you look at the pages that you have just mentioned, basically what you have is a table of integrals for formulas of different kind. It's not, well, there are another set of textbooks which have a more complete table of integrals. So this is not a handbook. But in any case, what you will see is, in order for you to check quickly, you have the form of the term, which is a plus bu, which is a linear term. And then you have related integrals that incorporate that form, right? All of these have an argument of the form a plus bu. So this incorporates the form square root of a squared plus u squared. So you have something positive, so you be mindful, and you have this. Then you have something of the form e squared minus u squared. I mean, if you think about it, well, basically this could be like a sine or a cosine if you do think trigonometrically, but that won't be part of this material. This is basically a hypotenuse. So you have different tables, etc., etc. So keep it in mind. It's possible that in some problems, especially the suggested problems, you might have to check on this. Yeah, okay. So u squared minus a squared is different. Exponential and the log, etc. So those are just 2 simple pages. There are more extensive books related to this, so this is just a brief comment. But so we will do an exercise where we'll use a table of integrals to find an integral of the form dx divided by 6 minus 3x squared. So From the presented forms, you kind of see what you have to choose. You have a factor of 3, you can factorize that. In fact, well, you have 1 divided by 6 minus 3x squared. This is 1/3. Then you have 1 divided by 2 minus x squared. So this could be put in the form 1/3, well, 1 square root of 2 squared minus x squared. And there is a formula related to that, which is formula 16, where you have something of the form a equal to square root of 2. And it just would be basically applying that formula. That's the whole idea. Look, it sounds boring, in a way it is, but the point is that there are books where you can go to when the integrals are not trivial. There are many ways to obtain different integration formulas. Some of them are trigonometric methods. Some of them are very ingenious. So if at some point it turns out to be pretty difficult, that is a good source in order to check. If you were to check that formula, and I know that you usually bring your textbook, so I will just plug in the formula. I will just put this in a nice fashion. So this is the integral of 1 divided by 6 minus 3x squared dx. So this is 1/3 of the integral of 1 divided by 2 minus x squared dx. This is 1/3 divided by the integral of the square root of 2 squared minus x squared dx. And then I can basically use the formula. So this is 1/3 divided by, or multiplied by 1 divided by 2 times the square root of 2. Be mindful of the a that we choose times the natural log of the square root of 2 plus x divided by the square root of 2 minus x plus a constant. And then the formula, which is basically formula 16, is the integral of du divided by a squared minus u squared is equal to 1/2a natural log of a plus u divided by a minus u, absolute value plus a constant. So this is just the evaluation where I have made a substitution, a equal to square root of 2. Okay? So there will be a new exercise, again using the tables. Of course, there are more modern resources for this. It really depends, on which discipline you are. But one typical textbook is, for example, ARFChem. There is also some Sham textbook where you could go to related to this. But in the next exercise, what we will see is an integral that is actually not in the table. So, if you look to find the integral of 1 over 3x squared plus 6 dx, so 1 over 3x squared plus 6, you can factorize again the 1/3. Then you have x squared plus the square root of 2 squared, because I have found the 2. So this is a form involving a squared plus u squared. So this is just basically to say that the table that you have in the book is not completely extensive. Okay? Think about the form that you have over here. And keep in mind this integral. Okay? Now let's go back to the table. In fact, look, there is a pretty good resource, not only in the books, but online, which is basically Wolfram Alpha. I'm pretty sure that you have used it before. So, okay, let's go back to, so you have here the square root of this, here you have, well, the formulas that could be easily related could be something like this, yet there is not an integral of that form. Okay. So in any case, going back, it's basically the short table of integrals in the pages 488 and 489. It doesn't have a formula for this. So there are some references, of course, for longer tables of integrals, which are, well, if you look in the book of Spiegel, Mathematical Handbook for Formulas and Tables. Look, I mean, this is kind of old school in a way. You're a student of the 21st century and your friend is Google. If it comes from a reputable resource, if actually it is an integral that can be computed, it will be there. Wolfram Alpha is a good resource. In fact, it comes from Mathematica. It's basically the online resource for that software. Having said that, there are integrals which cannot be analytically solved, and that is something that I mentioned 1 week ago, or 1 week and a half ago. If you look at elliptic integrals, it can be proved that you cannot have an analytic expression for that. So be mindful. You cannot be computing like crazy and then you realize that the problem has no solution. So the last example is basically to use the table of integrals, which is the integral of 1 divided by the square root of 4x squared minus 9 dx. And you would have to rewrite the term well, basically factorizing. So you have 4 times x squared minus 9 over 4. So you can take it, this is a 2. Then you have a square root of x squared minus 3 divided by 2 squared. So, in fact, your a, well, is such that a squared is equal to 9 over 4, which means that a is equal to 3 over 2. And this is actually in the form number 20, where you have, well, the integral of 1 divided by square root of 4x squared minus 9 dx, 1/2 of the integral x squared minus 3 over 2 squared dx. If I use the formula, this is 1/2 natural log of x plus square root of x squared minus 9 over 4. So then you have the square root, then the absolute value, and then you have a constant. So just look at the formula, and then you will see. There is a last application of this topic, which if you work in population biology, economics, you might find useful. So this is related to the logistic equation, which is a dpq of the form dq over dt equal to k times q times a factor n minus q. So, and k and m are constants, and the solution, which is of the form y equal to q of t, is called the logistic curve. This appears very frequently in population biology. Well, in fact, in population models in general. This is basically like a first-order correction of the Malthus model. If you think only on the first term, disregard the second. This would be like a Malthusian growth. You have a constant, and the rate of change of the population Q is proportional to Q. That means that you have infinite resources, and let's say you have bacteria. They reproduce often and often with a rate related to the coefficients, but that is assuming infinite resources. The correction that is in the logistics, so it's a first-order correction, is basically the first non-trivial model for populations. This is telling you, okay, the growth for values of Q small will be at an exponential rate, but at some point that growth will be equal to 0. That will be, if you think about it, when that factor is equal to 0, which means that Q is equal to n. So there is a limit to the growth. First, it starts at Malthusian, okay, an exponential model, and then you have a limit. The value of m is usually understood as a carrying capacity, because that is the value at which the dq over dt is 0, and then after that, you have a decrease. In fact, for values of q greater than n, that factor is negative, and then you have a decrease in the population. So, if you work in population models of any kind, that is something that comes up very often. So this is a model for, let's say, epidemics, populations with restricted growth, etc. In fact, well, all populations have restricted growth. You cannot have infinite resources, that is clear. If not, I mean, at some point you would deplete the resources, regarding talking about bacteria, for example. So the exercise is basically to use a logistic model for a propagation of a gossip. So use a logistic to study the spread of a rumor. So the information of the problem is that at 6 a.m., two executives hear a rumor that a new stock offering to be presented at noon. So the rumor spreads throughout the 26 junior executives of the firm, and you're given the rate. So 0.025 n times 26 minus n. And n, which is a function of time, is a variable that represents the number of executives who've heard a rumor T hours after 6 a.m. So, if you're going to do modeling, there are very many predicts of the model. First of all, executives are not a continuous variable, they are discrete. So this is a continuous model that is trying to approximate a discrete event. That is fine, in terms of the number of population. So the first indication is to find n as a function of t. And look, this is very similar to the DFQ problems that we did with separation of variables. So if you basically separate the variables, you have dn divided by n times 26 minus n, and then you have 0.025 dt. Then you integrate on both sides and you're done, right? So this is a constant, 0.025 t plus a constant of integration, which we're going to call C1. Then, well, look, of course, what is indicated in the textbook is that you could look at formula 6 with the values u equal n, a equal 26, b equal -1. That would be equal to 1 over 26 natural log of absolute value of n divided by 26 minus n. And, well, what you know by assumption is that n is less or equal to 26 because that is less than the number of executives, so that's why it was chosen as the carrying capacity. So this is 1 over 26 natural log of n divided by 26 minus n. And you don't need the absolute value precisely because of this constraint. So, look, in order to solve this, what you would have to take is basic course in DFQ. In a first course in differential equations, you will learn these techniques. For the purpose of the exercise, of course, it's pretty fair if you simply use the table of integrals. That's fine, that's not an issue. And in order to finalize the solution of the exercise, what you would have is natural log of n divided by 26 by minus n equal to, so you pass the factor of 26 times 0.025 times t plus this 26 times the constant C1. So if you do the computation, this is 0.65 times t plus, well, 26 C1. Then you would take the exponential, n divided by 26 minus n. So take the exponential of these factors, e to the 0.65t, e to the 26 times c1, which will be a constant c. So this is e times e 0.65 times t. So then you would have n equal to 26 minus n times c e 0.65 times t. And, well, you can actually do some manipulation. So if you pass this term to the other side, you have n times 1 plus c e 0.65 t equal to 26 c e 0.65 t. And we'll just finalize with this. N of t is 26 c e 0.65 t divided by 1 plus c e 0.65 t. And you determine c from the initial condition n of 0 equal to 2. So, okay, good luck and see you tomorrow.